this would be an awesome way to study for something. Like, test your knowledge by doing things like these. This is a great study technique. Okay, looking at it for those of you on the road, this is 4.6 that we are finishing up with. We just checked out the homework, and what we're going to try to do is make a nice little summary of what do we do when we actually graph these. So if you're watching this on the road, please take a second to pause, and I want you to fill out as much of this table as you can. Cool. I will give you guys a minute, and when we resume, we will see the constructed table. So here we go. 3, 2, 1. Going through here, because we have all of these transformations, which, Huggins, I agree with your statement, when you put all these pieces together, it does make it challenging. If we have them all written out, it's going to be essentially the same for each of these. I have a few things written a little bit different, however. Okay, right off the bat, Fern, you said 2 pi over b. Love it. Cosine is also 2 pi over b. Now, just in the interest of finishing this, what about tangent? Pi over b. And what about cotangent? Same thing. Now, if you need to make a note, I'm fine with it. And I don't know whether it fits best on this table on your trig cheat sheet. When I think about tangent, I think about the right half of my circle. That's my first interval that I want to deal with. It's the right half of my unit circle. When I think of cotangent, I think about the top half of the unit circle. Okay. Beyond that, in any of these situations, this looks a little bit different than what we've been doing, but is it? When we've found our jump, we always take the period that we get, and then we do what? Divide by 4. Could I have written divide by 4 here? Absolutely, but anytime that we get a value of b here, it makes it kind of bleh. So I'm just going to think about it as multiplying by 1/4, because it's easier to multiply than it is to divide. Cool. All right. What about for tangent? What would you do? What do you think, Mickey? No, 1/2. We want to cut it into 5 pieces, which requires 4 cuts. And that's a weird idea because remember, 1 cut cuts something into 2 pieces. So it's always 1 more. Okay, is it going to be any different for cotangent? Now, as you're dealing with this, a lot of the time you do wind up getting your b value as 1, and it winds up being convenient. But they're all the same approach. Cool. For this one, this is how I would recommend doing it. I know that sine and cosine, the easiest place to start at is 0. And it works because it's defined. This one's going to be a little bit different. When we think about tangent, I want to stress again, regular tangent, I'm thinking the right half of the circle. That's all the way from negative pi halves, or 3 pi halves, however you want to think about it, up to pi halves. So just the right side of the circle is where we're looking at for one period of it. We want to have x such that still, I'm going to use st as my shorthand, bx minus c, if it's just tangent, what do we want to set it equal to initially? Where's the first weird place that you have with tangent? Or more specifically, where's the first asymptote you're going to find? Negative pi halves. Now, if you don't want to deal with negative pi halves, you don't have to. You could start at pi halves and then just go a full period beyond that. This is much more common. Okay, I'm going to make one more really important comment right here. When you set this equal to it and get your x value, this is going to always spit out what value on your function. Like if I think of the tangent of negative pi halves, that's negative 1, sorry, am I right here? Yeah, I'm right. It's going to be, there's an issue with it. Undefined. Okay. Similar, but slightly different this time with tangent and cotangent. You're still going to take your argument, which is this bx minus c, whatever it is. But this time, where's the first asymptote on cotangent? 0. And again, I'm just going to say it's undefined. You could write VA for vertical asymptote if you'd rather, but it's the same idea here. Okay, this one's a little bit harder because it's not all real numbers. I'm just going to, it gets kind of ugly based on this because we don't have a general rule if we start moving stuff around. Would you agree with that? So when we're looking at this, all you're going to have to do is say left asymptote. So I'll say left vertical asymptote, which is this point, right, where we're undefined. I'm trying to think, is there a better way to write this? We're already committed, so we're just going to roll with this. Left asymptote and right asymptote excluded. That is a clunky statement. Now, the reason I'm having issues with the clunkiness is because I'm trying to avoid making it the super ugly version. I know that it's going to be all x such that bx minus c is not equal to pi halves plus pi over b. That's awful. If you wanted the real formal version, the set of all x such that x is not equal to, and this is a smaller set within it, x such that bx minus c equals negative pi halves plus n pi over b. That statement is just ugly. But that's the same thing that we just said. Everything except the asymptotes. But that's an ugly math statement. I would not write this one. That probably doesn't help a ton. Cool. Now, I'm not going to write it here because it's the same thing, left and right asymptotes excluded. Cool. I don't think I want to include the secant and the cosecant because we're just going to graph sine and cosine and then draw parabolas on them. Anyway. All right. Hopefully this is helpful and will be helpful when we do it. This is the simple summary of everything that we've done the last several days. All right. Anybody in here have a wood stove at home? Or you've used a wood stove? You've seen a wood stove? Do you know what a damper is? Okay, so on a wood stove and most burning stoves, there's a way to increase or decrease the amount of air so that you get more oxygen, bigger, hotter fire, or less oxygen so it burns slower and cooler. That is called a damper. That's what it's called. To dampen something as opposed to make it moist is to try to control it to some level. So if I go to a monster truck show for spring break, which I am doing, I'm going to put ear protection in to dampen the noise. They're not really noise canceling headphones, they're noise dampening headphones, but that sounds less advertisable. I don't know the word there. Okay. In any regard, we are going to be doing some damping today. And this is the last section of 4.6. So, we've looked in 4.6, just as a quick review, we did the graph of tangent and cotangent, we did secant and cosecant, we did this whole summary piece, and now we're going to look at what we refer to as damped trig functions. And these, legitimately, I think are going to be the coolest graphs you've ever seen. Cool. They're not the coolest graphs that exist, but they are cool. Damped trig functions. Now, to inhibit or to restrict something is a good way to think about damping. Now, turns out when we're really looking at this, what's going to happen is we will restrict a function, and we'll say it f of x, by multiplication with another function, g of x. Now, we've already seen the impact of this a little bit, but we can make them super duper cool. So, I want to look at our first one. We're going to just consider an example together, and I want us to try to think about what happens as we build up this function. So, here we go. First example, we're just going to define our function f of x is equal to x times the cosine of x. Now, this can be a challenge to think about, but we're going to look at Desmos and see if we can't make sense of it once we build our table. What is the largest possible value that x is ever going to become? Or sorry, on cosine. What's the largest output it's ever going to give us? Anywhere on the circle, the biggest thing that cosine of x is going to spit out is what? It's always 1, right? Can you tell me anywhere where that happens? So if I did, for example, and we're just building a small table, and we're not going to do infinitely many points, but we're going to see something awesome. If we have x, and we think about what happens with x times a cosine of x, and we just see what does it actually spit out at me, let's just build this up. And we're going to pick nice values, and we'll see how this relates back to these graphs. Okay, 0 is an easy one to do. When I plug in x into this function, you do not have to write all this unless you feel you need to, but do you agree that it becomes x times the cosine of 0? And what's the cosine of 0? So 0 times 1, it's 0. Everybody good with that? Okay, give me another nice value, and we're going to go a little bit further. I know at 0 it happens. I'm going to take a big step ahead. At 2 pi, if I plug in 2 pi for all these things, I would obtain 2 pi times the cosine of 2 pi. Do you all agree with that? Now, instead of writing the cosine of 2 pi here, what is the cosine of 2 pi? Check it out. Here I am. What's my cosine at 0 right now? I'm going to go 2 pi radians. What's my cosine here? So what's the cosine of 2 pi? Just 1, right? Now, whoever said 2 pi, if you multiply these, what do we get? 2 pi. Now, if I wanted to go, and I'm just picking arbitrary points here, if I picked 4 pi without actually doing the work, could you tell me what it's going to spit out at me? 4 pi. Okay, because I would see it's just 4 pi times the cosine of 4 pi, which is, again, just 1, and we get the same value. I want you to do one more for me, and let's do negative, and I'll just pick a nice value here. Let's try negative pi, we're doing cosine, right? Let's do negative pi thirds. Cool. So I'll trust your unit circle practice. Negative pi thirds. What's the cosine of negative pi thirds? So careful, I think you're at pi 6. Pi thirds is close to half. It's a half. Okay, so this becomes what when we actually do it? Now, I could do a ton of points here, right? But we're going to check something real quick. Do you guys see that there are very clearly 2 different functions up here? Now, I called it f, and maybe I should have called it something else. But notice, here's a function, f of x equals, or g of x equals x. And here's another trig function. This is just some function times another, right? Of those 2 functions, y equals x or y equals cosine x, which one's easier to graph? X, for sure, right? Now, as we look at it, we're going to see something awesome happen. Could you guys graph x if you needed to? I think so. So here's what I want us to look at, and we're just going to pop over to Desmos for a second. And damp, again, remind me, it means what? Not necessarily less. Restrict or control is what I really like. So check this out. If I graph y equals x, I know that's a line. Now, negative x also looks like this. And I'm just going to throw this in. We're not going to go into the nitty-gritties here. Those graphs are easy to make, right? Now, I know that at some points, whatever x I plug in, if I'm thinking x cosine x, it's going to be as big as x could possibly be. Like, it's never going to get bigger than that. And what I mean by that is when we graph this, check it out. I get a trig function. Now I can see it waves. It is a regular trig function. And beyond that, at all those nice values, like 2 pi, I see that it spits out a 2 pi. At 3 pi, where it was negative 1, it spits out a negative 3 pi. And I see that these are just completely contained within that graph. I have damped this trig function and controlled it to be stuck between these 2 functions. Now, you can get some awesome functions in doing this. X is pretty chill. X squared, it goes to the square of whatever the largest value is, and because it gets infinitely large really fast, it gets huge. But I can see that if we put the graph of x squared and negative x squared, I think it becomes a little bit more clear to see that, hey, look, it is in fact bouncing between those two functions. It is being damped or dampened by that restriction that we've put on it. Okay, we're going to do one more, and I want you to do a little bit of recall. I'm not going to give you crazy hardcore damped functions in this class, just so you're aware. But I do want to be able to think about them and think what happens. I want you guys to use a minute to think back to as much as you can. I want you to sketch. If you want to make a table, I'm fine with it. If you want to try to sketch it without a table, also fine with it. I want you to sketch the following function for me. I'm going to call it d of x because this thing's been damped by the following. I want us to consider e to the x, and I'll change color for the different function, times the sine of 4x. Cool. You are going to have to rely on each other. We've dealt with e to the x this year. If you don't remember what it looks like, your notes, your book will hook it up. Sine of 4x, how has that thing been changed? The period has changed. So instead of being 2 pi, what's the period of this thing? Pi has. Now there is an interesting question that goes beyond this, is I don't know if this thing is really periodic anymore. I don't know if I can pick up one little spot and paste it over because it keeps getting bigger or smaller, right? Cool. I want you guys to attempt to sketch this either by making a table or just remembering what stuff looks like. I'm going to give you a second. What graphs do I have on the board right now? E to the x is the top one, right? Why did I put negative e to the x on there, do you think? Sometimes sine is negative, right? So it's going to flip this over. So check this. As we look at it, I don't even have a scale yet. We're going to be able to reason it. I'm just going to start thinking. I'm not even going to put a scale on it since we're just sketching. If I start at 0, what's the sine of 0? Sine of 0, I'm pretty sure, is 0. Okay. Does sine typically start going upward or downward from there? Up. And it goes up until, in this case, it looks like it's going to be at pi fourths is where it's going to happen because I can see that the period has been changed. But I'm not even going to mark it. Do you agree that sine goes up until it hits 1, which is going to multiply by e to the x? It's then going to fall until it gets to a negative 1, which is going to be multiplied by e to the x again. And it's going to keep happening. My function gets taller and taller and taller because every time that I get to a bigger value, e to that bigger value is a bigger number. I see my function is completely stuck in between. As I work this direction, it's going to get squeezed into infinitely small space.
So why did you not only put the positive, like the exponential? Why did you put the decay?
Because for the fact that I know that sometimes it's going to be e to the x times a positive 1 gives me e to the x, but sometimes it's going to give me e to the x times a negative 1 because of what sine does,
Right.
which is just going to spit out this other lower bound for my function.
So even though like sine of, well, you don't have the x value, huh? Like in this, you're never going to get the x value. You're just graphing it without like.
Yep, you could get the x values for a better idea, but because we're just sketching, I'm fine with this. Now, if we want to see like a better picture of this and a more specific actual graph, we can bounce over to Desmos real quick. We'll get out of that craziness. We had e to the x cos x, right? Is it sine or cos?
Sorry.
E to the x times a cosine, sine of x, sorry. And check it out. It gets really big really fast. But
Ours was 4x.
e is sine, thank you. Okay, check it out. Here's what we just draw starting out, yeah? And then as I zoom in, it looks like it just becomes a line, right? Does it? Hey, look at that wave still waving. It's still going over and over and over. These things have huge applications, especially when you're dealing with things like noise sound waves, light waves, anything that travels in the form of a wave, which is like half of the universe, or more of it realistically, these things do show up all over the place in nature. Cool. All right. Should we do another one? Or are you okay with just saying they exist? Okay. I want you guys, last try, only a sketch, okay? Talk it out, reason it out, but you don't have to do like a formal table and stuff. As much work as I showed is sufficient. On this last one, I want us to think of a function, f of x, that is the sine of x acting as a damping factor on the cosine of x. Cool.